So knowing what you know about, just to get you started with this definite integral, knowing what you know about that definite integral, you want to first write this as what? How do you want to write that in order to make finding the definite integral a little easier?
Can you move it? Yeah, thank you.
I'm not sure I can. I think I might have to realign it before I do. Okay, so looking at that, gosh, there we go. World is working against me today. A little better. Okay, so looking at that, what's the first thing you want to do? How do you want to rewrite that, even before taking the antiderivative? How do you want to rewrite that? Okay, at the negative power. Remember, anytime we have x in an expression, you know you're going to do some sort of power rule. So you want to see the power, okay? Before you do anything else, you want to see that power. Okay, go ahead on your tables and do the antiderivative. Talk amongst yourselves. Discuss what's happening with the power rule. Here's some good conversation going on in the middle of the room. Oh, interesting. If power is negative 1, what is 1 bigger? Power is negative 1, what is 1 bigger?
So it's not supposed to make it sense. Okay.
If the power is already negative 1, what's 1 bigger? Where'd you get that? Hey, where'd you get that? But by increasing the power, how do you come up with that? Well, what's the new power? Well, I'm just saying, going on what you know, and I know you know some other things also. Okay. So who's running into a problem? I see a couple of correct answers, but we're just not there. You're just a step or two ahead of where I think the majority of us are. If we make power 1 bigger, what's the new power? It's 0. Well, can we evaluate? So big F of x, we have an x to the 0. But what do we need out front? coefficient of 1. What happens when we try to take the derivative of that?
Zero.
Yeah, we have to divide by 0. Is that a problem? It is a big problem, isn't it? We end up having to do this. Right, bring down the 0. If I try to take the derivative of this, I'd bring down my power, right? And then I would reduce this to the -1. But I get something undefined out front. That's a problem, right? That's a problem. We get something that's undefined out front. So we're going to approach this. And so far I've got 2 people who already have the right answer. Okay? And I might have more. I just know at first glance I know I've got 2. We have a problem in using the power rule. It's not working. Because we get something that's undefined out front. Which means we need to figure out what this is from a numerical standpoint. Kind of like we did when I asked you what the derivative of sine was, and we had no idea. So I said, let's graph the derivative values. Remember that? Okay. So we're going to. So what I want you to do is we know we need some antiderivative evaluated at 8. And we know we need some antiderivative evaluated at 1. We just don't know what that antiderivative is. We know it's represented here. The antiderivative is represented as what on this graph? If this is my function, 1 over x, the antiderivative is represented how on this graph? The area, right? So if here is 1, 2, 3, 4, 5, 6, 7, 8, and here is 8, then we have the antiderivative evaluated at 8 is the area accumulated to 8. What is the antiderivative evaluated at 1? Whoops. How much is the antiderivative evaluated at 1? It's 0. I mean, how much is colored in under the graph from 0 to 1? Nothing. Does that make sense? So we know that the antiderivative evaluated at 1 is 0 because we don't have anything colored in yet. Does that make sense? Okay. So there's nothing colored in. Well, yeah, but we're only evaluating it from 8 to 1. Okay. So let's go ahead and take the antiderivative at each one of these values. Okay, so we're going to use an f-int here. Okay, remember how to do that from your graph screen on your calculator? Okay, so why don't we go ahead and let's do this. Why don't you do x equals 1, f-int, okay? You're going to do an f-int x equals 2. X equals 3, do an f-int, 4, 5, 6, and 7, okay? And just get that number up there, okay? You're going to do an f-int on 1 over x. Okay, go ahead and write it up there. When you get the number, go ahead and write it up there. So each one just has 1 data point. Let me know if you need help on doing that. You're going from 1 to 5. Okay, so you're going from 1 to 5, and then the function is 1 over x. Okay?
How many does it go around into?
3. Let's do the AP standard of 3. So when we're putting this in, you're putting in from 1 to your answer, 1 over x dx. And you're getting an answer that's going right here. That's what that little thing in blue says. Okay? So we're gonna. So you put a 6 in the box, yep, and a 3 on the. 3 decimals. Oh, you were, yes. And then. Yep, 3 decimals. 1 point something something something. Okay. This is, this is AP standard, right? 3 decimals. Yeah. So that's it. Okay.
Just want to make sure I
And
can do it
we've got some function graphs, and as we're putting numbers up here, lo and behold, OMG, we put tables on our function graphs at the beginning of the year. So let's try to figure out which function this is. It's one of those on the wall. So if you notice, the graphs on the wall are labeled 1 through 8. Okay? The lower numbered graphs are oscillating or have real small numbers, grow slowly. The graphs on the other end of the spectrum grow fast. Match the table. Which function is the antiderivative of 1 over x?
right. I want to do it from the graphs.
Which table does it match?
Fine.
I agree. Talk to your table. Which one does it match? Do we have a graph that it matches? Do you have a graph as to which one it matches? Do you know which one it matches? Comparing the tables? You got tables right up there. Do we know which one it matches? So, which one? What, pardon me? LOG. Okay, so the LOG is this green table here. And my Y values in that green table are 0, 0.3, 0.47.
Just kidding, Li.
Okay,
That one, natural log.
here's the natural log. The values in this table are 0.60, 0.693, 0.1099. Are those getting closer? Yeah. So we see these values as the natural log of the absolute value of x. Notice how all the x values ended up being positive. So you guys had 1, right? So think about accumulating, starting at 1 and ending at 1. We get 0 area, right? 0 area accumulated. Okay. So just numerically, we see that this ends up being the natural log of the absolute value of x. The value of that antiderivative at 1 is 0. So we can simplify that by just calling it the natural log of the absolute value of x. Okay, so we know that the antiderivative of 1 over x dx, and you notice right now I didn't write an upper and a lower bound at all. Okay, because we're kind of going in that direction where we're just looking to find an expression for the antiderivative. Okay, last chapter you were actually evaluating it at 2 points. Okay, which means that was a definite integral. It had a definite beginning and a definite end to the area we wanted to accumulate. The difference here is we're just finding an expression, we're not evaluating it. So you are actually doing more work in chapter 5 than you do in section 6.1 in chapter 6. Okay, we're just looking for the function. How are we doing so far? Doing okay? So remember we learned, in fact we did this back in chapter 3. We said what's the derivative of natural log, and we didn't know. So we graphed it and we got 1 over x. Do you remember that inquiry activity? So this is reversing that process. Taking the antiderivative is reversing the process of the derivative. So if we started out, and we know we can't evaluate the natural log unless x is positive. Okay, if you look at the graph, right, the natural log graph only exists for positive values of x. Okay, so in chapter 3, let me kind of erase that. There we go. In chapter 3, we learned that the derivative of the natural log was 1 over x. And in chapter 6, we learned that the antiderivative of 1 over x when we looked at it numerically ended up being the natural log of x. We just reversed that process. Does that make sense? Okay. Okay. It's not the whole story, but it's the beginning of the story. So looking to tell the whole story, I want to look back at, remember this function? We all know and love it. We've been looking at it for like half a chapter. I just keep picking it apart. What was the antiderivative here?
Still a 6.
I'm not sure what you're saying. What's the antiderivative here? This is our derivative.
Yeah.
T to the fourth.
What? Yeah. What did you say? 1/4?
1/2.
1/2 t to the 4th. Okay. Right. Bump up the power, and then we've got to make the coefficient out front whatever it needs to be to get a 2 when we bring down that new power. Remember that? Okay. So, and we've done this problem. Let's see. This is saying evaluate the antiderivative where? Where do I evaluate the antiderivative if these are my upper and lower bounds? Right? And we've actually done this problem before. Okay, we said let's make this kind of like a definite integral. We have a lower and an upper bound. Okay, and so evaluating the antiderivative at x just means doing what?
Switching a t for x.
Exactly, switching a t for x. And then evaluating this at -1 gets us what?
1/2.
Okay, so we ended up with this constant here. And remember, this is when we were talking about the plot rule. We said, let's take the derivative of this, and what happened to the 1/2? If we took the derivative of this,
1/2 goes away.
1/2 goes away, right? Because it's just a constant. So what if, subtle change here, almost identical for this next definite integral down here, except that the lower limit, the lower bound is 0. So what does this end up being? Yeah, okay. Antiderivative at x minus antiderivative at 0. So what does that end up looking like? 1/2 x to the 4th minus 0. Right? If I plug in 0, I get 0. Right? What's the derivative of this? Is it the same as this or is it different? It's the same. Right? Because if I take the derivative of 0 is 0. The derivative of 1/2 is 0. Right? What if I subtly change it and I have the lower bound at 2? I still have that, right? That's the upper bound. Evaluate at x and evaluate at 2. Yeah, now when I throw 2 in there, I get 8. What happens when I take the derivative of this? It's the same thing, right? What happens if I change the lower bound to, okay, yeah, so we end up, we just, every time we change the lower bound, we just end up changing what aspect of this function?
The
The constant. Ooh, 3 to the 4th. What was that, 81?
Yeah.
81 over 2. Okay. We just end up changing that constant that hangs off the end. But if I would take the derivative of all of those derivatives would be what? The same, right? In fact, they would all be 2t cubed or 2x cubed, right? Okay. So the idea is this: when we talk about an antiderivative, and I'm going to be really careful with my verbiage here, because we call the antiderivative a bunch of different things. We call it an indefinite integral. Think about the opposite of indefinite. The opposite of indefinite is what? Definite. Definite integrals have what? Upper and lower bound. So indefinites don't have an upper and lower bound. They're gone. We're just doing the antiderivative for the sake of finding the function. Does that make sense? But we know that depending upon where the function begins, we could have a different number hanging off the end. Does that make sense? Does that make sense?
Yeah.
So when we do an indefinite integral, this is also called an antiderivative. Okay, that's another word for it. It's also called a general solution to a differential equation for reasons we'll get into next week. Okay, those are all the same thing as an antiderivative or an indefinite integral. When we do an indefinite integral, we're just looking for that function. And we need to acknowledge that depending upon where we begin, we might have a negative half off the end, we might have a 0 off the end, we might have an 8 off the end, we might have a minus 81 over 2 off the end. In other words, we might have some random what? What are all those numbers called? Okay, well, yeah, and Nick just said all those numbers are called C because he scrolled down a little bit. Okay, that's always good to look ahead. So we call those random numbers arbitrary, actually, is what the book wants to call them. We call them constants, right? They're all constant values. So what we do is when we find the antiderivative, the big F, right? That's our antiderivative. Then at the end, we stick what we call an arbitrary constant. And that just acknowledges that we don't know where we're starting and we don't know where we're ending, but we know that wherever we start, we're going to get a constant. Okay? And so we call this an arbitrary constant. So long story short, just keep finding antiderivatives the way you've always found antiderivatives, and then we're not going to worry about evaluating them, so we have a lot less math to do. Hooray for that. Okay, got less math to do, we're just going to throw a plus C on the end. Okay? So any questions about that? Okay, so let's try this. The antiderivative then of 2x cubed is what? Yep, 1/2 x to the 4th plus c. So we're just acknowledging that c could be a 0. It could be a minus 1/2. It could be a minus 81 over 2. Could be a plus 4. Doesn't matter. Okay? So if you think about it, we've been finding antiderivatives, right? Since 5.3. Really, we did a little bit before 4, actually. It's nothing more than reversing your derivative rules. You've been doing that. And then we're just going to look at more antiderivatives other than what we've been discussing. Okay, before we go to that page, here are the ways for me to ask this question. Evaluate the integral. And then they would give you a integral of 2x cubed dx. Find the general solution for the differential equation. Means the same thing. We'll talk more about differential equations next week. Find the antiderivative. Same question, different verbs or different verbiage. Find the indefinite integral. Same question, different way of saying it. Okay? So those are all saying the same thing. How are we doing so far? Doing okay? All right, so this is right out of your book. These are your derivative and your antiderivative rules written in a general sense. Okay? So I really like this one. I think this one, I've been kind of having you do the antiderivative the hard way. All of chapter 5, I've been saying, find that number out front that you need in order to make something. Okay, in general terms, all we need to do is find the new power and divide by the new power. That's all you really have to do. So let's try this. Find the antiderivative of 2x cubed dx. What's your new power? We know we can bring out the 2. That's our properties we learned in chapter 5. What's the new power I need for the antiderivative?
4.
My new power is 4, right? All I really need to do is divide by 4. So it's 2, new power is 4, divide by the new power. Does that give me my 1/2?
Yeah.
There it is. Okay, so you can think a little less on trying to get that coefficient. Just make sure you divide by the new power. Okay, it makes it a little quicker. Here's the one we discovered. This is the one we just did numerically. We found all of the antiderivative values of 1 over x. We found out it ended up looking like natural log of x. Okay, this is the derivative rule from chapter 3. So these are all from chapter 3 basically. Okay, and then we've got some rules down here. Notice we have this k. Like, this k is just a number like sine of 3x. So these are all dealing with chain rules. Okay, when we have something more complicated than just an x. We've got a k, and we've got like a 3x or a 5/2 x or something. Okay, notice we're still just dividing by that coefficient. Okay, so that's reversing the chain rule. Remember the chain rule, we said sine of 3x would be cosine 3x times 3. Well, if we do the antiderivative, we're just finding the antiderivative and dividing by the 3, reversing that process. Okay, and then these are always important. Down below are your trigonometric rules. Honestly, if we look at this row, memorize, because you'll find it on a no calculator part. These rules, you'll have a calculator available to you. So you would just need to enter Nderiv. Does that make sense? Okay. In fact, if you know how to program your calculator, it's nice just to put them in a little program. I can show you how to do that. Okay. And just throw them right into a program with your calculator, so that they're there, so that you can call them up. Okay? Any questions? So, same as section 5.3, we just don't have to evaluate it. We're looking at antiderivatives here. That's what happens when those upper and lower bounds disappear. I've got a 6-1 day 1 homework that I'm going to give you a good 25 minutes to start on. Each question really is just a minute or 2. You should be able to finish that right here in class.